It's a pleasure to have with us Professor Ayse Coskun from Boston University. Professor Coskun was invited to be a part of this by Professor Mohammed Bakir from Georgia Tech, so we thank him for that connection. Just a little bit about her background. She has her bachelor's degree in microelectronics engineering from Sabancı University in Turkey. Hopefully I pronounced that correct. And then a master's and PhD in computer science and engineering from UC San Diego, during which time she also interned at Sun Microsystems. She moved to Boston University in 2009 and is currently an associate professor in the Department of Electrical and Computer Engineering. She is an associate editor of IEEE Transactions on Computer-Aided Design, as well as Transactions on Computers, and among many awards has won an NSF Career Award in 2012. And I'm going to hand it over to her to begin her presentation. And again, thank you for joining us today.
Thank you for the introduction, and thanks to Mohammed for inviting me. I am Ayse Coskun. I'm at Boston University. I'm an associate professor there at the moment. And this work I'm going to present has been done in collaboration with my colleague, Professor Ajay Joshi, who is also a Georgia Tech alum, and also our PhD students, of course. We have been collaborating with CR Leti in France, and some of the work has been in collaboration with folks at UCSD. So today I'm going to talk about how to use 2.5D actually systems with silicon photonic networks as a way to build energy efficient systems. And the key approach or vision we have to do this is to do a cross-layer optimization, and I'm going to specify what that means. So obviously the trend has been that we keep integrating more cores into our processors. This has been going on for several decades now, and while it's fun, it's not easy to build large chips with hundreds of cores potentially. So we've seen this trend, especially in the last decade or so, going from a few cores to tens of cores, and now we are talking about potentially hundreds of cores. Now, one way to build many core systems in a more practical way, in a more sustainable way in some ways, is to go with a chiplet-based approach. Basically, as opposed to putting all the cores in one chip, one could design a bunch of chiplets and then integrate all the chiplets together. And people might be familiar with DARPA CHIPS program that started a few years ago, and there are other programs, of course, that are along the same similar lines. And DARPA CHIPS program, for instance, was about designing a whole bunch of somewhat standard interfaces for making this chiplet-based integration easier. Now, this is basically what's happening, and we believe this is one way to continue the efficiency trend and reclaim some of the dark silicon that has been an ongoing problem. Basically, we can put a lot of silicon out there, we can put a lot of transistors in our silicon, but keeping them all up and maintaining the efficiency targets that we want has been a primary challenge. Now, what can 2.5D integration bring to the table? So 2.5D integration can mean a whole bunch of things, of course, but broadly it refers to having some sort of an interposer and a whole bunch of chiplets integrated on top of it. This gives higher yield because as opposed to building one big chip, you can make smaller chiplets and you can have a more robust integration process. Cost-wise, it can be advantageous in some cases, and it provides an easier way to put heterogeneous technologies together. Logic and memory, silicon and silicon photonics, and other things. So the pictures from IBM from some time ago, actually, but the vision is still there. So you can put together a photonic network layer, a memory layer, processor layer, all together in a system like this. Now, compared to 3D, a major advantage of 2.5D is regarding thermal. So 3D integration increases the amount of heat generated in the same footprint, obviously. So 2.5D doesn't have the problem of stacking too many layers on top of each other. So thermal-wise, it's easier to manage. And there are substantial cost advantages as of today. Now, then, is this sufficient? We just, switch to 2.5D chiplet-based design and we achieve lower cost energy efficient big chips. We hope so, but we believe there are some important challenges to be resolved to achieve this vision, to realize this vision. So the questions we've been asking in the last few years in our project has been, one of them is like, is there a need for some new network technology and architectures? Basically, how do we build this with silicon photonics particularly? And then how about things like thermal sensitivity and its impact on the overall system energy? For instance, Interposer can have the silicon photonic network that can connect a bunch of chiplets in a high-speed manner, high-speed, high bandwidth. But then the devices, silicon photonic devices, are sensitive to temperature. So if we don't solve this problem, then that adds to the power cost because of, the variations need to be maintained. So overall, the end goal should be having an energy efficient system, not just doing 2.5D. So we believe these challenges need to be solved to be able to achieve, as I was saying, to realize that vision. This is a nanotech speaker series, so many of the attendees might be experts in device technology. I'm not a device person, so that's a disclaimer. But if you have device-related questions, feel free to shoot them, and I will make sure to answer them in the best way possible. But I can look for answers offline as well. But in case some people are not working with silicon photonic technology, so when we say silicon photonic link, we are talking about a laser source that could be on chip or off chip, and we receive input through a driver and ring modulator, and the light travels through the waveguide and propagates into an output where there's another micro ring resonator, a filter essentially. It goes through a photodetector and has amplified, and of course, the necessary electrical optical conversion circuitry has to be there to connect this into the electrical circuit. Now, at a high level, what are the advantages of using silicon photonic technology? It provides a lot higher bandwidth density, and it can provide lower long-distance communication latency. So especially when we are thinking about building a big chip using 2.5D technology with a whole bunch of chiplets connected on an interposer, longer distance communication latency can become an advantage. And the data-dependent energy consumption is much lower or negligible even compared to electrical links. Now, there are some disadvantages or some challenges that come with silicon photonics technology, and they are sensitive to thermal variations and as well as process variations. Now, what this means is that, variations, we know variations, we live with variations, even in the electrical circuit domain, right? But here, what it means is that it's going to require higher thermal tuning power if you have a lot of variations in your system, because at the end of the day, the communicating rings will need to resonate at the same frequency, so some of these devices need to be heated up. And same thing with dealing with process variations. So one will have to be taking care of process variations so that communication is robust on the system. And this high thermal tuning power can grow, especially for large chips, if not taken care of. And other challenges include high optical losses, especially if there's a lot of longer links or lots of turns and crossovers, etc. And the laser source efficiency remains low. And we are talking about wall plug efficiencies of 15% in good cases, I believe. So if efficiency is a problem, then one could increase the laser source power, but then that adds to the overall power consumption of the system. So if the end goal is getting the best performance per watt we are spending out of the system as a whole, we need to consider all of these things as a whole. So one could design silicon photonic network on chips. NOC here stands for network on chip, using several different ways. One could do monolithic integration, 2.5D, 3D. And there are some pros and cons with each one of these techniques. Like I mentioned, we are in this project have been focusing on mostly 2.5D. We see that as a more practical way of integrating things at a reasonable cost, and we believe this is higher impact as of now. But if you have thoughts on monolithic 3D having certain advantages, I would love to hear them. Particularly with silicon photonic networks. So we are focusing on 2.5D. but many of the things we are doing could apply to monolithic and die-stack 3D as well. Now, as I mentioned before, like at the very beginning, our key vision is to look at the system as a whole and design system-level optimization to help achieve this energy efficiency improvement target. And what does system level mean? Basically, a system has many things. It has devices that are basically providing the technology. People build circuits with them. People build architectures on top of these circuits. There's a system operating on top of these architecture, and then there are applications running, user applications that come and leverage these resources. Now, much of the work overall, when you look into silicon photonics networks on chips or 2.5D or 3D integration, looks into one or maybe two of these layers to optimize something over there. Our work, in contrast, is advocating basically modeling this entire stack so that you can see what happens to, for instance, device thermal sensitivity if you run a particular application on it. Or what happens to your overall energy efficiency if you spend so much power in thermal tuning. So we believe by looking into this system as a whole, one can understand things better, but also potentially improve on some of the aspects without leaving optimization opportunities on the table. So we want to actually achieve more by having this type of a system level view. And specifically, we've done several different things. We looked into design optimization. For instance, PNoc here refers to the silicon photonic network on chip. Optimizing the PNoc layout on a chip with a system level view, basically looking into all the way from the application all the way down to the device. And if you know what kind of power profiles you have, how would you optimize your layout? Similarly, we looked into cross-layer optimization of Nocs and 2.5D systems. We have done work in system management aspects. Basically, how would you manage your runtime system? For instance, allocate different applications threads into different cores to help with the thermal sensitivity issues. And lastly, we've done a bunch of work on PNoc power optimization, basically how to manage the power consumption of the associated with the silicon photonic network so that the overall energy efficiency gain is higher. In this talk, I'll mostly talk about the PNoc power optimization, and then I'll come back and touch upon the other aspects that I just talked about. So a key ingredient to do system level optimization is to have a system level or across the stack model that can work with a variety of systems and architectures and technology assumptions, etc. So at the device level, we are interested in looking at the impact on the microring resonators. These are, as I mentioned briefly before, sensitive to thermal and process variations. So we need to model this impact. We need to model how much heating power is required to thermal tune these MMRs and the overall energy efficiency impact. So basically, we need to have the models for this, but we need to look at this model when we are actually, emulating some application running on the system. We need to look into the architectural impact. One could have different designs resulting in different data rates per wavelength, a different number of wavelengths, different number of waveguides, a variety of PNoc topologies. So this has to be taken into account in this simulation framework. And like I mentioned, we need to have an idea of what kind of applications are running on the system, because knowing the architecture is not sufficient to have a good idea on the power profile. You might already guess this, like in a high-end server, there's an average power consumption and a peak power consumption, and this gap is typically pretty high. As the system gets larger, this variation of the average case and worst case, best case, etc., in terms of power consumption, varies a lot. So we need to have an idea of what type of applications are leveraging the system. Now, at a high level, again, the simulation framework will then have some models regarding the devices, architectures, and systems you see in the middle. The device sensitivity models, thermal control loops, etc., need to be plugged in here, and similarly with architectural assumptions and the like. And the input would be the variation profiles, the architectures that we are tweaking, applications that we want to run, and other system settings. And the output we are interested in getting out of such a modeling framework is system performance, along with overall system power, but also specifically looking at PNoc power and thermal profiles. This PNoc power and thermal profile are interrelated. So depending on the thermal profile of the system, there's going to be a different PNoc power consumption because of the thermal tuning power, like I mentioned. Power and thermal are generally interrelated anyway. Even if you look into electrical system, you need to look at both together because of leakage power issues that is temperature dependent, for instance. So this is the overall simulation framework at a high level. I'll revisit this with some more details later on. So I keep mentioning thermal tuning power. So what happens with this thermal tuning business? The micro ring resonators are designed with a particular intent, but due to process variations and thermal variations, there's a shift from this frequency. So PV here shows process variation, TV here shows temperature variation. So then the idea is that, okay, there's some variations will happen. So one could then heat and then move this resonant frequency to a particular level where, the system is going to have still robust communication. Now, this is not new. I mean, people have been designing this. Basically, you put some sort of a heater and then using a Joule heating effect, you provide some heater driving current and heat up the ring. And our colleagues at Leti actually designed a nice analog control loop that has a feedback loop here. It compares the photocurrent with the reference current and adjusts at a fine granularity the current level. They demonstrated at ISSCC a couple of years ago. So more details are in that paper, and I can share more details if there's interest as well. So this works, albeit with some power overhead, like I mentioned, because of the additional current that needs to be put in to get the heat to a particular level to heat up this device. Now, maybe one parenthesis that we can discuss is that, through discussions with many colleagues who are designing devices, it's also possible to design devices that are athermal or, less sensitive to temperature. But then there are other issues. So actually having devices react to temperature is not a bad thing because process variations will happen one way or the other. So the thermal tuning is also a mechanism to alleviate the process variations so that you can actually safely operate in a technology that is prone to a lot of variation. So maybe, it's good to consider that. So anyway, we leverage this specific analog thermal control loop developed by Leti, but there are other examples out there. So the architecture or the overall system we have been working with is called POPSTAR. It's a photonic interposer-based Manycore system, originally developed in Leti in France. One of my PhD students, Aditya, contributed to the design and optimization of this particular system during a 6-month stay in France. It's the architecture that I was talking before. So our compute chiplets, there's a whole bunch of them, and then there are transceiver TXRX chiplets that are connecting the compute chiplets to the network. There's a silicon photonic interposer, and there's a waveguide going across the system. And these micro rings are organized in groups to enable the communication across different chiplets. The laser sources of chip in this case. Again, there are more details available in our recent publications in this POPSTAR architecture. Here's a more detailed version of the simulation framework, and we are happy to share parts of this if people want to do similar simulations. We intend to release already the part that is computing the heating, thermal tuning power and PNoc power and such. But even without public release, we can share some of the other pieces if there's interest. Just let me know via email what your project is and what you would want to do with it. So on the left side, you see the architecture level simulator, Sniper, which we modified for the purposes of this. If you have a different architecture level simulator, you can apply similar principles. Basically, what you need is a simulator that can run an application at the desired granularity. You can try out different thread combinations, different voltage frequency settings, and you can model your architecture on top of this, obviously. And this simulator should also know something about like how many laser wavelengths you have, because that's going to determine how much bandwidth you can provide on the system. And that's going to impact your performance overall, obviously. And then there's a network power model that we plugged in, which is looking into both electronics and laser power. And the logic power, the typical CPUs, caches, etc., these are coming from MACPath. We calibrate MACPath with for the types of cores and caches that we are using. And then on the top box that is in the red dashed box, the Hotspot 3D, which is a 3D extension of the commonly used thermal tool Hotspot, which my team had done some time ago. This Hotspot 3D is now used, configured for this POPSTAR layout and with all the material properties and thicknesses and such, so that it can provide the resulting temperatures. And you can choose the granularity that you want to play with. In this case, like you want to know, for instance, what's the temperature at a MMR ring group, basically. So once you know the ring group temperature, then there's a lot more you can do. Basically, then you can look into, okay, this is how much thermal tuning power I need to apply to get the rings to the same temperature. You can say, if my thread allocation changes, this is how the temperature changes, and then this is how much PNOC power I need to have, and so on and so forth. This system policies should be also aware of the heat efficiency and the process variations and other parameters that might be impacting your system. And overall, then you get the thermal tuning or heating power out of this. So you see on the left side or the middle side, electronics and laser power, you see the heating power, and all of these are combined to get the overall system power. And now, what do we do with this? Now, like we have a simulator that we can play with. Okay, we can run a Manycore system that's built in this chiplet fashion. So what do we do? So in this case, by the way, we experimented initially with 6 chiplets, each of which had 16 cores, I believe. But then we varied, that was the original design that LAT was looking into prototyping. And then in some papers, we varied the number of cores and chiplets and the like. So one key observation that we had once we had the simulator was that, when you're running different types of applications on your Manycore system, you get performance benefits out of, having more lambdas. Basically, having more lambdas means that you can have higher bandwidth communication. Some applications benefit from this more. So if you look into this plot on the left, you see that some applications execution time drops substantially as you increase the number of active lambdas. And in some other applications like that green line LU-cont or the Barnes application, etc., they see a more mild effect. So the reason for this is the application property. So some applications basically use the network more, and some applications use the network less. And actually, each application may have some variations within the application. I'll talk about that later. Now, one could think that, well, I'll just, design a system for applications that actually need the network. But often we design systems that are not doing just one task. We do a variety of tasks, and there will be some amount of variations. And the observation here is that if you provide more bandwidth into the system, some applications will benefit from it. For others, you will be wasting power, right? So, and if you provide more bandwidth, then the PNOC power increases. So what one can do is to exploit this observation and provide just enough bandwidth potentially to cut down some of the unnecessary power. And on the right side, you see the power increase as the active lambdas increase from 1 to 6 for this system. And logic power, in some cases, increases with higher performance, some cases stays more stable, but thermal tuning power in all of the cases increases, as you see, as the temperature is increasing. So to exploit this, what we did was to design a policy called WAVES that is coming from Wavelength Selection. And the purpose here is to identify the minimum number of photonic channels that satisfies the bandwidth requirements, given a threshold of performance, for instance. Like you can say, ideally, this is the highest performance one could get. I want only 1% lower than that at the lowest. Or you can say that, I'm less restricted about performance. I can get maybe 10% lower than the ideal performance, and then let's see what that brings in terms of the overall energy efficiency. And this wavelength selection has to account for thermal and process variations as well, because of the reasons we discussed before. So basically, as the temperature changes, as the process variations change, they will impact the resonant frequencies of the rings, and one need to compute the heating power and the like accordingly. I can't see the time, so I'm just gonna quickly.
You've got about another 20 minutes or so.
All right, sorry. Okay. All right, so the idea over here is going to be running waves to select the sufficient number of wavelengths while accounting for these overall system level view and the associated thermal variations and process variations. So how we did that initially was to, okay, we can profile the applications and see which wavelength serves best for them from this energy efficiency perspective. So here, the normalized PNoc power is basically when you activate all the wavelengths, all the lambdas you have, and you see several different choices. For instance, one of them is just providing 1% allowance for performance degradation. The blue bars allow for 5% degradation, and the red and orange bars provide a little bit more flexible performance budget with like 10% performance loss allowed here. And the applications are run with 48 threads. And these are, I forgot to say before, these are applications from Splash and Parsec benchmark suites that are popular in the architecture and design automation communities. Now, what we see over here is we have higher power savings for applications that are not very communication intensive. And the communication here is basically is going to be between cores and caches, essentially. So the more parallel an application is, it's going to require less communication. Like Black-Scholes is an example of that, the finance application that some of you may know of. So if the application doesn't require a lot of communication, it can save more because, intuitively, then you can turn off more lambdas and use less of the capabilities that you have in your silicon photonic network. So that's kind of obvious, but I think it's important to see. So also, obviously, if you have more allowance for performance loss, you can actually save more power and, achieve more efficiency. And then, actually, the two bars that says first lambda, best lambda. Best lambda is finding the best option. The first one is basically when it's doing the thermal tuning, it pushes everybody to have the same first lambda available. And we can discuss more about that if needed. So basically, if you have optimal wavelength selection that is considering the PV and TV, you can save more. So overall, when we looked into this, we achieved a good amount of performance. But keep in mind that this approach requires knowing your applications and profiling them in advance to decide what would be the best number of wavelengths to provide for each application. Now, one other thing that we considered is that while Parsec and Splash type of applications are popular in the community because they are benchmark suites that are open sourced and many people use them, they are not necessarily very memory intensive. And they weren't originally designed for the purpose of creating high traffic in the network either. So we looked at other applications, particularly graph applications, which is emerging in a number of different fields today. We basically used also the NAS parallel benchmark suite, which is a high performance computing application suite, and we increased the amount of bandwidth available in the system. And we saw that actually fraction of time spent in memory it drops substantially with these applications that are communication intensive. So for these type of applications, if you were to apply a technique like waves, basically select only the amount of lambda that is needed, the savings could be potentially higher. So that was the observation. And that's why we looked into graph applications in our paper earlier this year. And for instance, if you look into graph applications out of that figure, and here the figure is showing normalized photonic power compared to, again, having all the laser wavelengths activated. And there's the laser power, the electrical optical conversion power, which we also compute, and the thermal tuning power. And there are 3 different applications, for instance, breadth for search, etc. These are graph applications. And then there are different data sets, because depending on the data set, you get different results. And so one observation over here is that thermal tuning power, compared to the plot I was showing with the parsec and splash benchmark set, here is a much larger fraction of the overall photonic power. And then, for smaller graphs, you can actually execute with lower lambda and save power. As your system is going through different graph sizes, you can adjust this. And overall, we reached over 35% savings in power on graph applications. So this is important because whenever we look into a many-core system that is like hundreds of cores, many chiplets, silicon photonic technology, it's also important to think about like what applications are going to benefit from this type of system, or what applications will people need to run on these systems in the near future. And graph applications are very, important in many domains today, as I was saying, from important search to some of the AI applications and such. So it was promising to see this result. Now, one other thing is that while application to application, it's maybe more intuitive that the trends of the applications would change in terms of how much communication they want. Another aspect is like the application within itself is not going to consistently pound on the network. So here's a graph that's showing a few of the HPC benchmarks, high performance computing benchmarks. And this is packets transferred, how many packets are transferred over time. I mean, it's over intervals, but it's essentially over time. So you can see substantial ups and downs. Some are more stable, some are more dramatic, but there's a change. So that's one observation. The other observation is that it doesn't look random, right? So when you look into these graphs, it looks like there's some pattern, and this is also very commonly the case, especially in a domain like high performance computing, but in many other fields, because of the way we write code. Basically, we write loops. We write iterations of stuff, we build data structures and then do processing on them and then rebuild data structures. So there's a lot of repeating patterns in programs, in many programs today. So one could leverage this and do something better than just setting one static number of wavelengths across the application. Instead, one could adjust how much of these wavelengths are needed during operation at runtime. And this is the observation, so that we can design a policy now to fit this dynamic needs and periodicity, or a loose periodicity, let's say, of the application's bandwidth demands. So towards this end, we designed PROWAVES, which is basically waves policy again, but with a proactive component. And this one does dynamic wavelength selection, and it doesn't just know all the applications and profile them and select later. So this is more practical. Instead, what we do is that we looked into a whole bunch of different metrics that are telling us something about the network, and then we created some models, for instance, number of packets transferred and the like. And looking into these metrics, we determine which metrics give us a good idea of how much network bandwidth need there is from the application. And then, using these metrics, we created an ARIMA-based autoregression moving average-based model, which is going to learn what kind of, or train basically and learn what kind of lambda value is good for a certain number of network activity, and then use this to forecast into the future and predict what kind of lambda value or what kind of bandwidth should be provided to the application for the next interval. So you can do this at different periodicity. It depends on how quickly your application is changing. We selected fixed periods for now, but there are also techniques to figure out like how periodic your application is and adjust this sliding window essentially periodically, automatically. So here are real and forecasted values for the average latency. That's what we are predicting. Basically, blue is the simulated value, and the red value is the forecasted value. Of course, the more predictable the application is, that depends on the application's nature, you'll get better prediction results. But even if you mispredict, you don't actually, there could be an efficiency loss for a short interval, but we do correct our predictor if the predictions are not coming out accurate. So there could be efficiency loss, but there will not be any robustness issue because the thermal tuning is always there. So we are not messing with the thermal tuning, but by doing this type of system level policy, we are changing how many wavelengths are going to be active in the system. So overall, even if you mispredict, some efficiency will be lost, or for an application that's completely arbitrary or random behavior, you might choose not to predict. But for most applications, this is going to bring some benefits for adjusting your bandwidth on the fly. Now, when we look into power saving values, these applications are high performance computing applications with a good amount of network activity, actually. And the baseline is without any wavelength selection. And then the SO and the DO are dynamic oracle and static oracle. So basically, static oracle knows the application in advance, profiles it, and sets one wavelength. Dynamic oracle is going to know all the phases of the application in advance and pick the best lambda for every interval. So these oracle policies require heavy profiling in advance, and especially the dynamic oracle policy is not realistic to do this for every single application. And PROWAVES is the proactive policy which basically predicts the network activity or the latency hit and then selects the best lambda based on this prediction. So overall, what we see is compared to static versions of BASE, which is the original WAVES policy, we can get 20% lower power on average. And we are within 12% of dynamic oracle policy, which is unrealistic, but it's actually the optimal policy here. So I think a key message here is basically if we do this type of runtime management, and if we have an emulation environment where we can look into the system as a whole, coming from the application all the way to looking into the device sensitivities and how much thermal tuning power is needed, we can get additional power savings out of this system. One other idea that I want to kind of talk about without too much detail, but just to show that there might be more things to do across the layers is one could also go back to the application and instrument the application to help with this type of runtime management. For instance, we mentioned graph applications before. In a lot of graph applications, some algorithms converge after or converge on some of the graph nodes after certain iterations, and it doesn't have to process all the vertices. There are many algorithms like this where some approximation algorithms may fall into this category as well, that you can actually stop processing at some point if you reach a desired target. Now, the idea over here is that if you look at this left side figure, if you instrument your software, it can actually tell you at what point you will need to process fewer vertices and such in a graph, and that could be used to guide your wavelength selection policy. So you can tell actually from the software layer all the way to your mechanism in the firmware, I would say, to tune these wavelengths and say that this application phase is coming where the demand for the network is going to be much less, so you can tune your wavelengths accordingly. So on the right side, you see basically the number of packets dropping when you do this instrumentation and actually say, okay, you don't have to process the converged graphs anymore. Then the number of packets in the network drops, and the results of the application is not changed over here. So when this is done, we show the simple proof of concept, basically, that you can actually achieve 35% lower power consumption by doing this application instrumentation-assist into the waves in the PageRank algorithm. There's a lot more potentially open problems here. We just wanted to show this as an idea. This is not currently in our focus to work more on this, but if there are people interested, we can certainly discuss. Now, let me quickly check the time. I have a few more minutes, I think. So I want to briefly mention some of the other things that we've done in addition to PNoc power optimization. One type of approach we took was to do system management. Okay, you know, so far in the talk, I talked about changing the number of wavelengths in the silicon photonic network. So that's something that we are doing to the network with a system level view, but we are at the network level. So in system management, you can do other things. For instance, you can controlling threads in the operating system is already done for performance purposes. So we can leverage a control like that to help with, for instance, minimizing the thermal and process effects on the silicon photonic devices. So the idea here was to bring some ring awareness into workload allocation. And in this case, the workload allocator is given location of rings and some prior profiling of how much thermal impact would scheduling multiple threads around the ring would create. Basically, if I put a lot of active application threads around the ring, how many degrees will the temperature increase in that location? And you can, because this hardware doesn't change at runtime, you can actually profile the hardware and get some compact thermal models that tell you with pretty good accuracy about things like this. Like basically, if I put this much power in this corner, will it impact the ring temperature? So we derive these thermal models, and basically the idea would be there would be high impact to ring temperatures, of course, if you put a lot of threads in that corner or in that location. And if there are scheduled threads that are further away from a ring group, then the impact will be less. But all of that can be modeled in a compact model. And then you can basically, allocate workloads with this awareness in mind. So the purpose of the workload allocation would be then to have some sort of an equal effect on all of the rings, so that it's not like one of the ring groups is at much higher temperature, the other ones that are at lower temperature, but all of them are hit in the same way, more or less. And we can demonstrate it in this way. So let's say there's a laser source and 3 different ring groups over here, and every one of these ring groups and laser sources were designed with some target optical frequency in mind. But then, you know, some process variation happened in ring group 3 and 2, and so there's a shift over there. And now, you know, when you start allocating workload onto the system, workload is going to consume power and it's going to change the temperature. So if we do this frequency alignment idea that I just described, basically the high-level idea being allocate your workload, keeping an eye on like how much you are impacting the different ring groups, you can gain some. And on top of that, as opposed to pushing everybody to the same frequency, you can see who has the highest frequency, highest temperature and lowest frequency, and you can basically push everybody to that level. So for instance, like you allocated 1 thread, 2 threads, 3 threads, you are basically making the frequency lower, pushing the frequency to the left. And eventually, after the 4th thread, this is where you are. And then with the red arrows, we are showing basically everybody will have to come to the same frequency, and you do that by pushing everybody to the lowest frequency level. So in this way, you basically keep an eye on how much impact you have on the thermal while you are allocating different threads using your compact model. And then at the end, whoever has the highest temperature or lowest frequency, in other words, is going to be the base, and everybody will be pushed to that base. By doing this technique, applying this technique, we achieved substantial reductions using this Freck-Align technique. You can just look into the Freck-Align and AFT, which is this adaptive frequency tuning. We in a Manycore system, we got 60% basically reduction by just compared to just doing ring awareness. And overall, there's a lot of potential if you look into the system level in that way. So I'm not going to go with the different variations over here, but basically we tested with different number of cores, different policies and the like. But the key message was that by actually applying this frequency alignment and adaptive frequency tuning, you can get a lot lower power due to thermal tuning. Finally, I want to mention what one can do for design optimization, particularly in layout. One one thing to highlight is that PNoc power is not just thermal tuning power. It also has laser power and electrical, as I mentioned before. So we design an optimizer which gets all the constraints like number of cores, aspect ratios, etc. Typical floor plan optimizer would know these. And then it builds a compact thermal model of the system. And the output should be a floor plan of the PNoc with minimized power and area cost. And you can actually, if you see in the minimized equation in the middle, you can pick and choose how much weight you want to have to power versus area, which one is more important for you. But overall, you can have an optimized PNoc, taking into account all of these laser tuning and electrical optical conversion power. And how we do this is through this compact power model and the power profile applied to it, we can figure out how much impact there would be depending on where I place the ring groups, and how I place my overall PNoc route. Because for instance, like you can have a serpentine or a U-shaped, but the U-shaped is typically preferred because overall losses will be lower, and if you go back to the equation, the laser power will be less in that case. But then maybe sometimes doing some fashion of serpentine or some strange shape might be better for thermal. So that could be a trade-off. So that's why we look into all of them together. And we built this optimizer that's basically a mixed integer linear programming optimizer, works with a whole bunch of floor plan constraints, and it has all the power, thermal, etc. device properties. And depending on the power profile that we see on the chip, the resulting PNoc was in many cases U-shaped, but in some cases it ended up having these interesting photonic silicon photonic layouts. So this shows that basically having this, again, application to device level view can change how you are designing your system. And in the interest of time, I'm just going to very briefly mention this. So we've been also looking into how to organize the chiplets. Can I put them a little bit far away from each other without making the chip too large, because that helps with thermal. And we got interesting results. We built an optimizer where you can basically determine, like, this is the amount of cost, additional cost I'm willing to spend. In other words, that translates to how much white space you can leave on your chip. And you need to, of course, provide your temperature thresholds and how much power your chiplets are generating and all of this input. And our optimizer is going to give you a layout of where you are supposed to put your chiplets. And I'll skip this quickly. So the result is something like this, depending on the application and your budget of how much additional chip area you are willing to spend. You can get interesting results like this. So for instance, when you look into the left one, you are seeing chiplets, which are the red dots basically, and the layout further away from each other. In the middle ground, you are seeing chiplets that are clustered in 4 areas, and on the right side, you are seeing a layout where chiplets are close to each other. And obviously, the overall interposer area changes substantially. We don't imagine people to really design with so much white space as you see in the 41 millimeter case. But this is showing essentially there's an interesting trade-off, and one could leave a little bit of room in between the chiplets to reduce the thermal effects. And you can have in this way a higher performance and a lower cost potentially. And so I talked mostly about PNoc power optimization, but the key message here was to look into the system as a whole, going from application to operating system to architecture and then circuits and devices to be able to analyze the cross-cutting effects. And we believe there's additional power savings lying on the table if one does this. We actually think that this type of optimization is essential for achieving efficient integration of PNOCs and getting over the fact that, okay, there's high power consumption associated with these networks, but then that's manageable. But then perhaps one could integrate even in smaller systems silicon photonic networks for interesting applications and improve system energy efficiency. So some open problems one could think about. I mentioned graph processing, like graph applications doing a lot of memory operations. I think there's more to do there, and there's opportunities for architecture or application level innovations to look into how to optimize the system with silicon photonic links. We believe there's a lot of opportunity for heterogeneous computing because once you start putting CPUs, GPUs, memories, etc., there's going to be a lot more larger thermal variations between chiplets. And if these chiplets are communicating with each other, again, there will be a cost of thermal tuning and the like. So there's some interesting threads over there to explore. And finally, if you have a system like this, you have chiplets all connected through a silicon photonic interposer, and it can provide a lot of bandwidth. One big question we are looking at currently is that what does it do to the memory? Basically, what kind of memory chiplet architecture and memory management policy should be there to make the most out of this network? Because in the long run, it makes better sense to think about the architecture as a whole and not just replace the network with silicon photonics and not just increase the core count, but also look into how memory should be integrated. So we have some active work in this line. And I'd like to thank you for listening and thank my research group and collaborators. And if there are any questions, please shoot. Thank you.
Right. Thank you very much. Appreciate your taking the time to speak to us today. There actually are a number of questions in the Q&A box, and I'll read off as many as we can get to in the time we have. So Walter asks, how does the thermal tuning power compare to the power used for computation? Is it on the same order of magnitude, much more, or much less?
And it depends. So in the earlier work that we've done, looking into parsec splash type of applications, most of the power, I would say over 70%, was in computing, and less than 30%, in some cases much less, was in the photonic silicon photonic network power. But once we looked into these larger graph applications with a lot of activity in the network, that changed quite a bit. So then it became maybe the other way. Maybe over 50–60% of the power was being spent in the network. And I think that's the real target case for a Manycore system with silicon photonic, to look into these type of emerging applications that are complex. And currently they require many servers connected, etc. And one could bring all of that into the single chiplet with single system with many chiplets and a silicon photonic interposer, but then manage the silicon photonic power using some of these system level techniques to get that power consumption down.
Great. Srijit asks, since the transceiver chiplets are still connected to core using off-chip electrical IOs, how are we increasing the core chiplet to chiplet wavelength? Isn't it still limited by electrical IO bandwidth?
That's a great question. So I don't recall on top of my head how much bandwidth restriction that would impose. But we were generally, the applications were generally leveraging much less of the bandwidth available through the silicon photonic network. So perhaps that's why we didn't really run into that problem. But that could be an issue, especially if you want to have a terabyte bandwidth. And that's something that I will look into. And I don't know how to respond later on, but that's a great question. Maybe Shri could send me a quick email and I can respond.
Okay. Mohammed asks, you mentioned the use of hotspot for modeling the thermal maps. Can you comment on its capabilities and how accurate it is? Is this open source?
Yes, so original hotspot, of course, is open source, but what we did was to do a 3D extension of it. And it is open source. We placed it on our website, but eventually most of our updates for making the 3D options available got into the hotspot version 6 and beyond, has our updates. So in terms of accuracy, it's a compact model, and compact models are as accurate as the information you provide to them, meaning that typically the bottleneck of accuracy in a thermal tool is actually not the thermal part, thermal modeling part, but it's the power consumption part. So if you do have finer granularity power consumption available through your circuit, for instance, and you are able to pass that into the hotspot 3D, it would give very accurate results. I mean, like I would say within a degree or two type of accuracy overall. However, the problem with running with hotspot 3D in large systems like this, and you want to do fine granularity simulation, becomes convergence time. So if you want to divide everything into layers and little grid cells, etc., the simulation time starts shooting up. And that was a problem we saw in this line of work, which we managed, but then we saw even further problems when we were doing monolithic 3D simulation at detail. What we did now is to build a new thermal simulator, which has a compact modeling front end, so you can work as if you are working with hotspot, which is really convenient, therefore it's very widely used and successful. But the back end is a SPICE simulator. And with SPICE, you can adjust the granularity. You can actually take a full industrial standard cell level design and push that level of layout and power information into the simulator. And the SPICE backend, already parallelizable, results in like orders of magnitude faster simulation times. And we just put that in public space just a few weeks ago. I can send the link to Mannat, but it's called PACT. And we are welcoming any input. If people have needs that is not met by it, we are happy to work on them. So overall, I believe the accuracy of the thermal simulator is good, but as I was saying, if you are giving it very coarse-grained power maps, then it can't do anything with that.
Great. And we do have a number of other questions. I'm going to ask one more just for the sake of time. And if people do have questions that aren't answered, I encourage you to contact Ayse. You can certainly Google her at Boston University, and her email will come up there. Yes. So this last question is from Sheng Tao. For the wavelength selection technology, will the frequent laser on-off reduce the lifetime of the laser?
That's a great question, and I don't know. Yeah, so I don't know the basically thermal cycling of the lasers and how much that impacts. There could be some impact. We believe it's not going to be impacting it substantially because the amount of variation we are introducing is not very large. Generally, thermal cycling related failures are a big function of the delta T you have. So as a result, we don't expect substantial damage, but we don't have numbers to quantify it. But it's a great question, and we should look into it more. Thank you.
And I think with that, in the interest of time, so I'm sure people have other things in their day, but thank you, Ayse, for joining us again, and thank you, attendees. And hopefully we'll see you all in 2 weeks' time for the next Nano at Tech seminar. Thanks again, everybody. Have a great day.
Thank you very much. I appreciate it. Thank you.